Hi, I wanted to make a video today a little bit different. Most of the techniques I've used are kind of easy to do using, say, worldometers or the WHO, the data sets, capturing them relatively manually, then processing them in a spreadsheet and finding a simple pattern. Today, I just wanted to show you the output of something that the professional data science team here at CarolCap produced, looking at the kind of larger data sets that are available and the techniques that you can use if you've got those professional tools and that kind of level of analysis available to you. So there is bits of this that are done using essentially Python code or C# code. So you would need kind of data science programming experience in order to reproduce this. But hopefully from my other videos, there's no smoke and mirrors to it. The concepts here, although the data and the analysis is a little more upgrade, if you like, it's really easy to understand what we did. I mean, it's a very sort of practical idea. So we want to, in general, what are we trying to test? Like a lot of these videos, they're mostly about how do we establish the level of evidence around lockdown techniques and their impact on COVID-19. So we know that lockdown is incredibly expensive. We need to demonstrate quickly that it's got strong evidence for its efficacy, and that process is essentially failing. I mean, you'll see that in a number of my videos, how it kind of fails to pass these simple statistical tests. Now, what I want to do is to show you a test today which uses probably the most amount of data available in the world today in order to come to a conclusion. So when you look at this through the lens of the world, you can't really talk about lockdowns. You can talk about individual measures. So what do I mean by that? Well, there's this great research group at Oxford University that's gone through all the legal measures in the world, or most of them in, I think it's about 200 countries, and have analysed them to do with how severe their application is and what domain they're applied into. And they basically come up with, a series of really practical domains like school closures, stay-at-home requirements, or workplace closures, so having to work from home, or closing public events. So that could be rock concerts or parks, but also it can be cinemas, theatres, restaurants, etc. So it's categorized that, and then it's built a huge database of all of that information. So here's the site that I got it from. So bsg.ox.act.uk/research project/coronavirus government response tracker. Now, this you can download data from, but it also has a live tracker on there. And we can look at any country and we look at the overall severity. And then we can look at how that severity is varied over time. And we can probably go in and have a little, you could look at it in more detail. Now, I can simply show you the downloaded data, which is probably the best way to look at this. So here's the database that they've built. Fantastic that it is. Country, the country name, country codes, the date, every day since January 1st, school closures, workplace closures, cancelling public events, restrictions on gatherings, closing public transport, stay-at-home requirements, restrictions on internal movement, so that's within the country, where you're allowed to go. Could we go to Wales, for instance? And then international travel control, so travel bans. And then it gives, depending on the day, what level of restriction is involved. So it's sort of saying, look, none of these restrictions were put in place on January 1st. Not really surprising. If we go across to the right, we get a bunch of stringency measures. These are the ones that are to do with lockdown, the stringency index. There are other things to do with government response, economic input, etc. But what we're looking at is purely the stringency of lockdown. So that's one big data set. And the other big data set you can get hold of comes from the WHO. So if I go back to that page and I go to the WHO, this is the WHO site. You can click on any country. So click on China, for instance. We can then look at its curves. So this is cases on top, deaths below. That's daily and cumulative. Just go back to daily. This is where China hides, I think it's 17th of April, isn't it? Let's just scroll down. 16th of April, suddenly, no, 17th of April, somebody finds 1,290 deaths. So they're very mysterious how that gets added in. There's a lot of this that goes on in China where they find deaths, and there are even negative deaths you'll find on a lot of days. So lots of negative deaths in this data stream, really odd things. But we shouldn't get distracted. It's one of those interesting topics. The fact that we talk about China and lockdown the proof when a lot of the data is massaged, so very dangerous to use that. So you can download the WHO data. What does that look like? Very simple spreadsheet. Here it is. So again, we've got date, we've got country code, country, the region it's in, number of new cases, cumulative cases, new deaths, and cumulative deaths. And just to show you the scale of these databases, this is the WHO. If we scroll right down to the bottom, you can see there are 27,000 records of case death data in the world, which is, that's every single day, every single, 204 countries, I think it is, or 214 countries, a lot of different countries. And similarly, if we looked at the other data set, it's about 8,000, 9,000, again, of all those days on a number of countries, looking at their interventions. So lots and lots of data. So what can we do with this? Well, you can turn this into a scatter chart. Now, here's the data that we generated. So you can see country, date, severity, delta, and RA delta. So let me describe what we did. For every single, when scanned through the entire history of a country, we looked at when it changed their measures, which is the day in which new measures came into effect. Those measures had a severity delta, right? So that meant that on one day, you could go to the shops, the next day you couldn't go to the shops. So we took the severity index delta from that Oxford database on every day that a country changed it. Then we looked at the rate at which R was changing before and after the delta. So, I mean, the classic model would say, R would be going upwards, a constant trajectory of 2.5, so there would be very little change in R, so there would be a 0 factor there, but it would be upwards. And then if the measure came in and it turned it to 0.8, we get a gigantic change in the R rate, lots, and we'd have to really think about how their R rate had changed, right? Because obviously R rates don't move on the spot, there would be some kind of pattern, and that would cause a new kind of change in the R rate, and that would be the gradient change. So we get a dramatic drop in the gradient. It would become a negative gradient. Now, it could be that R was already dropping, and then it would drop faster, it was going up, and it would go up slower. It doesn't really matter how the R rate was moving. It's just about tracking that. And all we did was take the 7 days before and do a line of best fit on it, and the 14 days after and do a line of best fit, and then subtract the post rate. Let me get this right. Subtract the post rate from the pre rate, because we expect it to be more negative. So therefore, if you subtract the post from the pre, if it's had a positive impact, we'll get a positive score. Negative impact, negative score. Now, just to say, of course, there are random artifacts in there. So when something is positive or negative, we don't know whether that's caused by the intervention or not. The point is that if we go across enough interventions, we should be able to see a pattern. So 2 weeks following an intervention, there should be some sort of decrease in the R rate, or the rate at which R is going should get more and more negative compared with beforehand. So we can pick up the impact. Now, just to show you this database and just to find a country that you do know, hopefully it'll come up in a minute. It's Great Britain. There we go, I isolated it earlier. And then you can see the classic dates. 16th was where the government, told us that maybe we should work from home. 17th, I think there was some more work at home components. 21st, you can see it going up to 9.26. That's when the certain numbers of pubs and stuff are shut. And these are deltas, these are increments. So the day of the lockdown, we actually went up to a severity of about 74, but in one leap, we went up by 35 in that one day. And then we can see, look, here are the measures, finally increased closure of public transport, happened a few days later, went up another few points. And then, actually, this is us unwinding on the 13th of May, I think that's public transport reopening. So a series of measures here. So then what is the output of that? Well, the output of that, let me find that, is here. So what we can see here is a scatter chart built from all of that data. So just, working through, what we can see on the axes here first, so you know what's being plotted against what. On one side, so this axis here, this is the change in the R rate. So basically it's sort of saying, right, what does 0.1 mean? It means that for every day that passes before compared to between pre and post, the R rate is decreasing at 0.1 a day more after the lockdown or after the measure than before the measure. So a positive number there means that the R rate has been reduced or is reducing. So if we had a sudden drop, you might go, well, what happens in a sudden drop? What you get is you'd still get a measure. So you might say, right, the R rate was 2.5, dropped to 0.8 within 3 days and stayed there. Now, what we would measure there is a 2-week line of best fit. So that might, we're talking about a drop of 1.4 over 14 days. It might be twice as steep as that or a bit steeper than that. So you probably expect about 0.2 out of that kind of scenario. So the sort of region that we would be led to believe that, for instance, our lockdown should sit in is about 0.2, and it would be over here somewhere. That's what we would expect from it, right? So that's the amount of R rate change, and then on the other side you've got the severity. So the horizontal is the severity change. So what's this axis here? That's severity. So severity is what's calculated by Oxford University, and they're doing it on the basis of looking at each individual measure on those 8 dimensions. So that is things like school closures, workplace closures, travel bans, stay-at-home orders, all of this kind of stuff. They measure the severity of all of those, and then they have an algorithm that generates consistently for every single measure implemented in the world a severity index in terms of its total severity of lockdown, if you like. And then all we're doing is saying, right, let's plot the severity of lockdown against the R rate change. So as I said, what would we expect? Well, we would expect that our lockdown, which had the day that it occurred was a severity increase of 35, and we're expecting a crashing reduction in the R rate of 1.4. So we would expect our dot to be here. And in general, what we're expecting is there should be a trend line, therefore, think about it, that will go through that point, through the origin, and out the other side. And that would be our expectation. So what we're clearly seeing is not getting that expectation. It's definitely a mess. The color coding here, just to draw a little bit of attention to that, is just covering, here it is, the code, covering the different scales. So that's the average daily deaths in that outbreak. So the very, very red, bright red dots above 750, then you've got below 750 but above 500, and then below 500 but above 250, etc. The grey dots are the ones in small outbreaks. But I mean, to remember, small outbreak, a lot of Norwegian countries would never get outside of that really small category. So that means that you can see that it's not, isn't that the small outbreaks have got random patterns and the bigger outbreaks have got a consistent pattern because of, it could be a fair way to look at it. That's not what's going on. We've just got a blancmange effect. Now we can zoom in a bit to have a look a bit more closely. And again, if I draw that expected line based on our kind of expectations of lockdown, that would look like that in this picture. So again, it's really, really clear. I mean, what's interesting is obviously most things are below that line, but if this is the 0 line, this is the line of no impact here, and things are above and below. Now, that doesn't mean the lockdown is is causing the negative impacts. What it means is that the other impacts, which are causing positive and negative effects, are completely outweighing any impact of lockdown. Given the strength of what we're expecting to see, that's pretty conclusive that lockdown is either having a very modest impact or no impact. You can't say it's having a strong impact, because if it's having a strong impact, it should be more clear. We can go in even closer and we can really see what a mess this is. Our measure now should be probably going almost like, oopsie, should be almost going like this across the chart. And, we are nowhere near that kind of scenario. So very, very clear that the correlations we're expecting don't work. Now, another place you could go to is to say, well, look, this is a mixture of every single type of correlation. What if we looked at, maybe the fact that you're scoring in school closures is causing a problem, because maybe school closures don't work, but stay-at-home orders do. But what we can do with this data set is to zoom in on every single dimension and then have a look at it. We can go one by one. So this is school closures. Let's just take a quick look. So because there are much less grades, you get these kind of vertical lines as opposed to a big spread. But what you'll notice from these vertical lines is that they are literally top to bottom balanced on 0 pretty much. So what does that tell us? That tells us that there is no correlation again. If we take the 0 line from left to right, we discover that everything is pretty much evenly balanced up and down from that point. We've got one school closure that seems to correlate in a big place with things closing up. But generally, we're just seeing a blancmange, and 1 point, given the rest of the data in the image, we can't really judge anything off that one extraneous point. So that's school closures, perhaps what we would expect least to work. Then we look at workplace. I think we'd expect that to be quite big. Hold on a minute, that point isn't really a point. That would be quite big, but it isn't. Yeah, sorry, this school closure, I made a mistake. I put a point in there. There isn't even an aberrant point. There's just no sign of anything. If we look at workplace closures, exactly the same problem. Let's put in the up and down, the 0 line. We can see up and down. It's balanced, really. We're not seeing anything that's telling us either way that this is making any difference. Closing of public events. Let me change that 0 line so we can see it properly. And again, we can clearly see balanced up and down, it's the same. And again, if we just look, restrictions on gatherings, no evidence there. This is the closure of public transport. Doesn't seem to be doing much. And this is the one that perhaps is the most important of them all, is the stay-at-home restrictions. And again, we don't see anything. There are a couple more bits to this: stay-at-home restrictions, internal movement. So that's not being able to go to Wales, for instance, which I'm not sure how many internal restrictions we had, but some countries did. Italy, for instance, locked down areas, and traveling between areas was problematic. And then you have travel bans. So flying somewhere in the world. So the totality of that, if I just go back to the original image, is that is 884 or 5 measures out of 2,000. Why can't we cover the whole 2,000? Either they are in countries where there aren't any deaths, in which case you can't do any robust statistical analysis. That's probably about 300 of those. Most of them, though, are just because most measures are unwinding measures, because we jumped into lockdown in a big jump. And then we've come out slowly in many stages. So there are many more unwinding measures than winding measures. The unwinding measures are only just coming in. As you can see, there's very few on the left here compared to the right. They're the unwinding versus the winding measures. Since that's the case, because it's so recent, we need to safely do this calculation. We need 37 days of deaths data post the implementation. 23 days for infection to death, and 14 days to do the line of best effect. So it takes 37 days to do the analysis. Therefore, basically anything that wasn't done by first week of June, we can't analyze yet. We can certainly come back to this image in a month's time and see a lot more of the unwinding measures. But we're looking at 80% of the winding measures into this, and so to find no pattern in such a large sample, particularly a sample that is only based at the level of the going into it from the fact that there are deaths and a measurable outbreak to test against. So we're not cutting back for some other reason. It's just simply that people put in measures where there weren't actually any deaths, and therefore it's very hard to do any analysis. To see nothing it's staggering. I think I would say I'm shocked. Although I never thought lockdown could deliver on the promises, it was in practicalities around the key workers being outside of lockdown and the sheer quantity of them, and the fact that the virus would spread through a third of the population or something. I never bought the 94, 98%, I'll be honest. But I did think it would have some impact, despite its flaws. And I think discovering an absolute zero of impact is quite shocking. But something whether we understand it or not, and we definitely don't understand it fully. A wall is hard. If you walk into it, it's still hard, even if you don't understand the quantum mechanics of why you can't walk through a wall. It's common sense. Walls are hard. You walk into them, it hurts. We're put in a lockdown. We trashed our economies. We caused massive social issues, and we're not seeing the commensurate results in our rate movements with this virus, which is telling us we just walked into a wall and it hurt. And we need to pay attention to that. So I hope that video was interesting, and thank you for listening.